Now, what do I get out of all of this? Well, the obvious things out of this are energy efficiency. If you think of battery life, for example, if you're using your laptops and codes are not doing something, we obviously shut them off, power goes down, battery life improves. Obvious. Similarly, if you have a data center or server farm which isn't doing much right now, but is having snoops going on, for example, again, power can be reduced by shutting these things off. These are fairly obvious kind of things, and they are very, very important. But given the first part we are introducing right now, which are at the high end, I do want to explain how we can put all of this back into performance if people want that. And that's the idea of turbo mode. So the idea here is that if you have, let's say, in this case, 4 cores in a system, and you find that you are running a lightly threaded workload, the power control unit can understand that, then what it does is it looks for the operating system to understand if the applications actually desire high performance. And if that happens to be true, then we shut the power gates, turn the power off from the cores which are idle. Then the power control unit takes the power headroom it got, it shifts it back to the cores which are active and want the performance, and it converts all of that power headroom into performance headroom, and you basically get high performance. It can work with 3 cores working, 1 core idle, or any combination, 2 cores working, 2 cores idle, 1 core working, 3 cores, any combination like these, they all work. What we get at the end of this is, if you're running a highly multi-thread application, you get good performance. If you're running single-thread application, you get good performance. So this is the whole balance I was talking about at the beginning, giving you good performance and good energy efficiency at the same time. Okay, I keep going down in the levels of abstraction. Started with platform architecture, went to CPU architecture, then to this power management stuff. Now let me talk about the next level down, which is chip design. So, when you want to go for energy efficiency and look for what are the big ideas, or what's what are the heavy hitters in terms of energy efficiency, we find that scalability is it. If you want very high performance, the simplest thing you can do is run your chip at very high voltage, right? If you want very, very good energy efficiency, you want to run your chips at the lowest possible voltage. And this range is this headroom between max voltage and min voltages, which we want to be as much as possible. Unfortunately, what's happening is physics is running against us. Modern processors don't really want to do that. So what are the problems we face with modern processors in this area? As we go for smaller and smaller transistors, the oxide gets smaller and smaller and thinner. They can't really sustain very high voltages. The transistors will fry up, so we can't have very high voltage because of that. Also, when we are building smaller and smaller transistors, we get other problems like soft error rates, variation in these transistors, etc., because of which the low voltages don't scale. So when you take this stuff into account, what starts happening is the range between the Vmin and the Vmax, if you want to think of that, starts shrinking. We don't have much left there. And similarly, if you look at this from a power and performance point of view, the headroom we have between the power and performance starts shrinking. This is a problem for us because that's what a process technology wants to do, which is essentially give you a max and min voltage which are roughly at the same point. Not good. Okay, so the passive approach to this problem would have been, well, that's what physics says, we can't do much about it, we'll deal with it, or you go at it. The gains you can get in energy efficiency are so much that we decide to go at it. And so let me just talk to that. If you think about the concept level, right, what's happening is performance goes with kind of with frequency, which goes kind of with voltage. So roughly performance is linear with voltages, okay? Power goes with cube of voltages. So now what is energy efficiency? Energy efficiency really is the ratio of performance and power, right? So if you do the math, it turns out that energy efficiency goes inversely with the square of voltages. That's a very powerful insight, which is that if you really want to go after energy efficiency, lowering your voltages is probably the biggest thing you can do, okay? So this gain is so big that we can't just let physics dictate it and not do anything about it. So this has been a massive amount of innovation in Nehalem to go after this problem and make the voltage scale. Okay, so how have we gone after that? The first thing was we have gone after trying to understand at a fundamental level what stops our chips from working at low voltages, right? And we find that it's very straightforward. The circuits which stop at low voltages are all memory circuits. Every circuit which has an uninterrupted feedback is a circuit which stops at low voltages. So we have gone after memory. One of the things we have done about memory, the first thing we have done is a very sophisticated error correction algorithm. When memory circuits stop working, what happens is some of the bits fail. So there are some errors. But if you're able to seamlessly correct these errors, so no one sees it, well, there's no issue, right? It's fine. That's what we have done with a very sophisticated error correction algorithm. The next thing we have done is we have decoupled the power supplies. So the cores can keep going down in low voltages for energy efficiency, and the cache can stay at high voltage, and everybody's happy, right? So we have done that. The one which perhaps was the most controversial was we can do this around the CPU cores. What do we do with CPU cores themselves? Traditionally, the memory arrays in a CPU core, which are things like your first level caches, the instruction cache, the data cache, etc., have traditionally been built using SRAM, fixed transistor SRAM. These structures have remained basically the same for about 40 years. If you go back to the 70s, they were still being built that way, right? Because they are the smaller structures you can build. We had a major decision to make. If we kept going that way, we could not get our voltages to go down. So we made the hard call to go with a new circuit technology called 8-transistor SRAM for the cores themselves. This decouples the read and write operations and lets you go to lower voltages and much better power efficiency because of that. Okay, next thing I want to talk about is circuit technology. This is the lowest level of abstraction I'll talk about today. Before talking about what we have done for Nehalem, I want to give you a slight history tour on these questions of power and energy efficiency, etc. So most people who have started with the semiconductor industry in the last 10 years think of power as a new problem. We have this power wall which happened in the 2000s, and we have all of these energy problems and stuff. But for people who have studied this problem long enough or have worked long enough, this is a cyclic problem. It's not just the first time this is happening. In the 70s, we had a major crisis in terms of power, not just for the oil crisis, but in the area of semiconductors themselves. At that time, all your high-performance computers used to be built using bipolar transistors. So if you go back to, say, an old Cray supercomputer, right, it used to be built using bipolar transistors. Now, bipolar transistors were extremely fast, but they were extremely power hungry. They used to consume power all the time, whether they were doing any work or not. So the industry ran into this brick wall of power in the 70s, and for the next 20 years or so, the big innovation was static CMOS. The whole industry converted to static CMOS, and essentially power took a nosedive, and the problem did not really appear till almost the early 2000s, right? So what's the problem? We should be fine, right? The problem was static CMOS inherently is fairly slow. So when we started going for high and high performance in the 90s, people kept inventing new and new circuit technologies, new way of designing chips, which were faster. There were things like Domino or the circuit technology used in Pentium 4, for example. Each of these circuit technologies was somewhat faster than, say, static CMOS, but it was at an exponential nature of power. It kept burning more and more power. So when we started Nehalem, we again looked at this problem and said, look, we can keep doing what we are doing or change innovation away from this. So we decided to make a hard call and go back to static CMOS, do essentially a full circle in terms of energy efficiency, go to the most energy efficient circuit technology known, okay? Now we had a hard problem, which is how we get back performance. So here what we did was, we shifted our focus of innovation from circuit technology to architecture and logic. We basically went and changed the algorithms behind key ideas in x86 architecture, like, say, instruction decoding, how we decode instructions, for example. So we shifted the innovation. At the end of the day, what we got back out of this was, we haven't lost any performance, we kept the frequencies, we got back to the most energy efficient circuit technology known.